So we're going to talk about why detection, why do we need gas detectors, how do we use the monitors, what we can detect with our monitors. We're going to talk about the methodology of detection. We're going to talk about LEL monitors, combustible gas monitors, toxics, VOCs, what a VOC is, what does our VOC monitor detect, and what doesn't a VOC monitor detect. We'll talk a little bit about what we do with all the data, and then we're going to overview briefly the MSA Sirius and some of the hiccups that we have with that, and hopefully with a standardized class and everybody's getting the same information, we'll all do it the same way. And then we'll talk about the race systems, which is the new monitor.
So this isn't replacing, this is adding on.
This is adding on. Yeah. Until such point as all the MSAs die. So I know right now we have 2 MSAs without a PID that are turned off. I've got parts on order for those. We'll see if that actually works to get those back in service.
413's arrived, 305 will be turned by their command.
So why gas detection? For our own personal safety. If we don't know the atmosphere is hazardous, to us, we'll walk in and become a victim, just like the victims laying there. As leaders, we have to protect our personnel for the same reasons. We don't want to send them downrange, our personnel downrange without correct ensemble. Full SCBA and turnout gear is our initial action on that. For the safety of the citizenry, obviously we all took this job because we wanted a cushy 24-hour gig with 10 days a month, but in the long haul, our job is to protect the citizenry, and if we don't know what they've been exposed to with our gas monitors, we're going to become victims as well. And then because the government tells us so, there's a ton of CFRs and federal laws that govern what we do for environmental quality, and it's essentially the me, you, them, us approach to safety and gas detection. So we're taking care of me first, then you as my crew, them the public, and then the government. So we're going to get back, bring the environment back to baseline, to normal. This video just illustrates why gas detection.
Go ahead. Yeah, plus 1, 2, I'll be 1023 to 1050. Possibly have fire, I get the smoke. Here we got 1 victim down the road, possibly 1 in the car. I'll be needing some assistance. What's the ETA on fire and ambulance?
1222 Effingham, 10-4. 10 Monday Alma Fire Department advised ETA 5 minutes, ambulance 5 to 7 minutes.
2210-4, advise ambulance and EMS to expedite. I'll be on the car checking victims.
2210-4. Oh, 61 Effingham, 1020.
Based on it's our rural area, it's a white cylinder on wheels, more like it's in high school. We're going to talk about ammonia pretty quick. It's one of our nasty
I don't remember how much experience that he had. He was a senior guy.
Bob Lane Googled this and he said it was a training facility. It looks pretty old, and based on some of the other information, I don't think it's a training video, but either way, it illustrates it pretty good.
Well, I think it was that.
Good, I thought it was great. That's what Bob Googled and found it, but as you know, Google isn't always right, so regardless, it illustrates a decent video.
That was my understanding was that.
My understanding is actually so you got the officer ran up to check on the victims, he became incapacitated, and now you hear fire on its way. So as fire gets here, look at, there's very small plume of gas, and they actually get out, fortunately in full SCBA, thinking that it's a fire because they do see smoke.
Yeah, it goes to that.
Exactly.
Oh, they've had a lot of training.
You couldn't read that, the microphone's cut stream uphill, upwind, but it would be just a tad close to my We'll talk about why in just a minute. So fire pretty much does the exact correct thing other than how close they pull up. They come off the truck full SCBA. The only thing that I might have done differently is gotten things going a little bit faster.
They probably pulled up that close thinking it was fire though,
Exactly.
not a gas.
But
I
you'll
think
see
he
your
reported that he had smoke.
smoke.
That was on fire.
Right. So they eventually get a fog stream on this to make once they realize that it's not on fire. And then they start getting close.
We really don't need a fog stream technical solution with these guys.
Exactly. The only other issue you have is that ammonia is flammable.
Correct. Quick wrestle on those guys. Wrestling is good.
That's why with hazmat IQ now, a lot of what we do is to investigate. Our estimates are very few. And the turnout gear protects us from explosive. So that's pretty much it. So that's why we detect, obviously. If that police officer wouldn't have pulled up on scene, if he'd have had a gas monitor going, he might have been able to see that the parts per million were well above toxic levels. If the fire crew would have pulled up and seen that, they would have known immediately that they were above their explosive levels and above their toxic levels. We'll talk about ammonia in just a little bit. The neat thing about it, or the neat or interesting thing about ammonia is it's placarded as an oxidizer. And actually that was something that the farmers did way back when they first started putting ammonia on farm fields. Is farmers, initially they were placarded as flammable, but because people didn't want to drive down the road behind a farmer and see this flammable cylinder, or parked out in the field with a flammable cylinder just parked there, they didn't want it to say flammable. And then they said, well, okay, we won't placard it as flammable, we'll placard it as toxic. And then farmers said, well, wait, I don't want people knowing that I'm putting poison, toxics, on my farm field. So then the farmers got together with Congress and they said that ammonia can be labeled as an oxidizer. So just be careful, if you pull up on one, it's going to have a green triangle as an oxidizer, not a flammable or a toxic. So anyway, talking about our monitors a little bit, so that's why gas detection. I will talk about how to keep them working. We want to talk about powering them on prior to entering hot zones. Van Hall and I kind of go round and round and back and forth on this issue. I think it's absolutely okay to fire them up in the cabs, especially our parts per million ones, which we'll talk about later. But you're not going to get the exposure to those monitors in those cabs off the truck driving down the road at 50 miles an hour. It does help to crack a window. Obviously, they have wrist lanyards on them for a reason. Put those around your wrists if you're going to hold the nozzle out the window. Crack it just enough to get a good airflow, and then you can zero them out at that way too, en route. And that'd be more than likely the guy in the back doing that. So make sure we're zeroing out prior to entering hot zones. We need to become familiar with our monitors. We need to learn our high alarms and what our low alarms are. Jay, can you tell me what your low alarms are right now?
For what?
For CO.
50.
Nope.
TWA is 50.
How about oxygen? Does anybody know?
19.5.
Okay. So, but we need to become familiar with those, and that's what we're going to do today. We're going to talk about highs and lows alarms.
CO's 35.
Okay. We want to handle them with care. They're not fireman proof. These were actually designed for industry use. Guys in lab coats checking leaky valves. They're intrinsically safe, and they're made to kind of drop a little bit, but we don't want to be dropping them on purpose. We don't want to be handling them as firemen. We want to handle them as protecting them as much as possible. We want to calibrate when they're instructed. The MSAs will actually tell you every 30 days. They'll tell you every day you power them on how many days are left until calibration. And we want to do that. We want to power on daily and bring to zero. And this is a big point, and I think a lot of people haven't heard this before, but take them out into fresh air. Don't power them on and zero them out while you're in the back of the cab. That's stagnant air. You want to go outside, outside in the fresh air, even on a day like today where it's raining, because all the sensors that we'll talk about in a little bit are based on temperature and humidity. Temperature and humidity affects what they detect. So if, say this morning it was 70 degrees out and humidity was about 100, it's going to say, okay, this is my zero at this temperature, at this humidity. And the same reason why when you go outside at 2 p.m. and it's 90 degrees at 50% humidity, it's going to calculate that in, and it works within the sensor's electrolytes to give you your parts per million and your percentages, and even a little bit of humidity trapped in it from, say, you took it out in the morning, you took it outside in this temperature and humidity, but then at 2 o'clock, when you go out at 90 degrees at 50% humidity and you don't zero it, it's still going to be zeroed for the humidity and temperature that you powered it on and zeroed it either earlier this morning or yesterday or 2 days ago. So that's why that's so important. And make sure that you're in fresh air. You don't want to be standing by running exhaust, especially when you get off the truck, kind of, figure out you're not standing next to the diesel exhaust of the truck. Keep the batteries charged. Monitor the zero after use. This is another big point is, even when we calibrate the monitor, we pull it off the calibration station, and then we take it somewhere and we set it for 30 minutes and let it run, let it purge itself. As you'll see in a little bit, there's electrolytes in there. They trap that gas, trap those chemicals. So we want to make sure that we run it and let it purge. It doesn't hurt to cycle the batteries. If you're running it so long, you get caught on a call, you come back to it and it's dead, that's great. Throw it on the charger. It's perfect for a lithium ion to purge the battery and bring it back up. So hazmat ops do approach from uphill, upwind, upstream, and decontaminate appropriately. They're water resistant to splash, but do not soak. They're not your Casio watch. They're not 50 millimeters or 50 meters resistant, underwater running. It's basically splash. Because anything that gets inside them, we just had one that got soaked with something, or something was soaked up through the air inlet. It breached the water membrane, it breached the particulate membrane, and it ruined the monitor. So just don't soak, decontaminate appropriately. Pretty well wrung out hot soapy water cloth to the outside of the case when it's powered off, and or alcohol preps if it's contaminated. But remember, we shouldn't be dropping these in anything. Don't drop them in water or mud. That goes along with it. If you drop them in that, make sure you're powering them off pretty quickly and give them decon. Don't suck up liquids. They're gas monitors. They're not liquid samplers. Okay. So even if you're remote monitoring with your probe wand and your tubing, don't dip it into something. It'll suck that up and will ruin our monitors. They're not product samplers. Don't power down without purging. We talked about that a little bit. So you go into a toxic CO environment, you find some CO in somebody's basement, you come outside, it zeroes down to zero, don't power it off. Wait till you get back to the station, let it run. It's not going to hurt that monitor to let it run. Those batteries last a long time. And don't use without the filters. That's going to become more important when we talk about the race systems, because the filters are removable by us, whereas the MSAs have an internal filter that pretty much I only mess with. Don't decontaminate powered on. Don't expose to extreme heat or cold. We talked about how they're sensitive to temperature and humidity. It's the same reason. Don't put them in a freezer, and they shouldn't be going into a fire environment anyway. Don't open the case in a hazard environment. In other words, don't change the battery. Don't open up the case and change filters. It's intrinsically safe when it's closed. And then don't change the battery in a hazard environment. Talk about gas detection procedures. We want to move slow. So we get called out for something toxic, nasty. This is about the pace that you want to be moving. It takes that much time for the gas to enter the monitor, it to do its mental thinking, and then spit out a result. If we're walking, at a rapid rate like this, you're going to walk into the hot zone through the warm zone, and you're not even going to know it. And then you're going to alarm in the hot zone. Okay? So we want to move slow. We want to vary the height of detection. Some gases rise in air, some gases sink in air. So we want to make sure that we're checking basements, attics, crawl spaces, things that, where it might hang low or it might go up into the atmosphere. And then use our probe wands for confined space areas where they cannot be easily reached. And remember that our pumps run at about 1 foot per minute. So when it starts at the end of a 20-foot probe, it's going to take 20 minutes to get to your pump and give you an accurate reading. Okay? So just remember that. The longer you are away from the pump inside the machine with that probe wand, the longer it takes to get.
What size are the wands?
And then there's also for the new one, there's a little jobby like that. And for the MSA, there's a coil, typically 10 feet, 8 feet, something like that. All right, so what can we detect? We can detect combustible gases. It comes out as our LELs, or our lower explosive limits. We can detect toxic gases, our COs, our hydrogen sulfides, our hydrogen cyanides. Oxygen actually falls into a toxic gas. That's there. VOCs are volatile organic compounds. We'll talk in depth about those and how do we detect them with those two monitors. All right, before we get into combustible gas sensors, if everybody can pull out their the NIOSH sheet with a box on it. We're going to talk a little bit about, should be this one right here, about what you find in your NIOSH guide. All right, so open your NIOSH guide, doesn't matter to what page, just somewhere in the middle. You're going to find 4 chemicals per 2 pages, so 2 on each page. And then if you look at this sheet here, we're going to kind of go through column by column of what each is. So in the upper left, you've got your chemical name. That's the name that everybody goes by typically. If it's toluene, they're called toluene up there. If it's, I don't know, acetylene will be up in that blue box. After that, to the right is your chemical formula. That's for those chemists of you that want to know how many carbons are in there and how many oxygens and that kind of thing. And the CAS number, that's that orange placard number that you might find on rail or some trucks. Your RETEX number is a registry of toxic chemicals. Probably won't see that number except for maybe on an MSDS. Okay? And then your IDLH. This one's a huge one for us, especially once we talk about our parts per million and our toxics and our volatile organic compounds. So we're going to use that box a lot. Conversion, don't worry about. That's basically how you convert 1 part per million to micrograms squared or whatever the chemical might be coming in. Your dot number is to the left of that. And the big highlight there is that's going to be your guidebook number. So your orange dot guidebooks that we go by for that first 30 seconds to a minute, that's the dot number for there. And the other point to that is if it has a P in the dot number, it means it polymerizes. And that's just a hazard warning to us saying this thing could go boom on its own. Okay, it could spontaneously combust or mix with something like air and combust. So that's just, that P means it polymerizes it. It changes its chemical properties on its own under pressure or with air. Okay? Next one is the exposure limits. That's where you're going to find your NIOSH and OSHA, PELs, RELs, STELs, TWAs. Lots of acronyms, basically. Relative exposure limit is your RELs. Your PEL is permissible exposure limits. Time-weighted allowance. STEL is short-term exposure limits. But that basically tells you all those numbers correlate to a 10-hour workday over a 40-hour work week. So that's what you can be exposed to each day over that 40-hour week without toxic, nasty stuff happening to you. That's what they say. I wouldn't want to expose myself to any of it. Then it goes to a physical description. I've always wondered how they come up with these physical descriptions, especially for like hydrogen cyanide. It smells like bitter almonds. I think what they did was they had a syringe of amyl nitrate ready to go, and they exposed a guy to hydrogen cyanide, and they said, "Tell us everything you know about it." And then all of a sudden he goes in the room with hydrogen cyanide and he says, "Bitter almonds!" And they shoot him with the amyl nitrate, and amyl nitrate is a antidote for hydrogen cyanide. So then he comes back up and says, oh, it smells like bitter almonds. I have no idea, but somebody figured out that it smells like bitter almonds. But that's where you'll find that kind of stuff. The physical, that's the physical description. And then to the left of that is your measurement methods. You won't have to worry about that as ops level guys. And then the chemical properties on this sheet actually goes with your box, where this starts with molecular weight. So this sheet's a little bit wrong, but you can see where it says chemical and physical properties. It starts with molecular weight. Molecular weight is in reference to air. Air we know is 29. Anything larger than 29 in the molecular weight is heavier than air. So Ryan, what chemical do you have on your page that you're open up to?
Chlorine dioxide.
And what's its molecular weight?
67.5.
Is it heavier or lighter than air?
That would be heavier than air.
Heavier than air. How about Mike? What you got?
I got another, the ones I got here are all heavier than everybody. I got one, kaolin, on page 183, and it says molecular weight varies.
Okay. Yep. And you might see some weird stuff like that. And it's just it's based on its mixture. It's based on whether it's a liquid or a solid, and it's also based on what container it's in. So you might get some weird stuff like that in there. Boiling point. We all know what boiling point is. It's the point at which it boils. Solubility. It's going to tell you there a percentage. It's going to tell you miscible, or it's going to tell you soluble, or it's going to tell you varies. So percentage means this amount will mix with water. Miscible is mixable, means soluble, and soluble means soluble. Or it'll say unsoluble. The next one is flash point, and that's up here. And the way I remember flash point, if everybody can see it, it's the point at which liquid flames. In other words, it's at the point or temperature at which a liquid on the ground produces enough gas above it in order to sustain combustion. Okay, so that's the flash point, the point at which liquid burns or flames. Your ionization potential, that's huge for us because it's based on what we can, I'll put it this way, what we can monitor is based on that number there in the ionization potential when it comes to our VOCs.
So this chemical here is a flash point of 118 Fahrenheit, but a boiling point of 325. So if it's boiling,
it's ready.
It's ready to flash.
Yep.
The vapors above it
Absolutely.
would flash.
Yep. And before it ever became boiling, if it was laying on the ground in a, what did it say? In a 118 degree day, it's already creating enough vapors on the ground that it'll flash. So Vegas was 120 not too long ago. That chemical was on the ground. It was ready to combust right now. It was giving off vapors at that temperature to burn. Okay. So IP, what's an IP you got there?
9.85.
9.85 EV. Our bulbs are 10.6 in our monitors, and I'll talk about what a bulb is and how it does what it does. But we need to remember that 10.6 is the magic number for us. Anything below 10.6, we can pick up with our PID. Anything above 10.6, we're never going to see. There aren't too many above 10.6, and that's why we chose a 10.6. They also make a 9.8, they make an 11.4 bulb as well, but they're a lot more expensive and they don't last as long. So after ionization potential is specific gravity. Specific gravity, if it has one, is comparing it to water. Water is 1. So if your specific gravity is larger than 1, it's going to sink in water. If it doesn't have a specific gravity, it may mix with water. If it's smaller than 1, it's going to rise to the top on water. So oil is probably going to have a less than 1 specific gravity.
So again, just so I can try to keep this straight in my head for this minute only, I'm sure.
Sure.
The molecular weight on this one is 112, so it's going to sink in air, so it's going to cover the ground.
Yep.
But its specific gravity is 0.93, so it's going to float on top of the water.
Yes, just barely. All right. We're starting to learn that we can glean a lot about the chemical properties from this book. It's pretty huge. Our gas D, you may or may not see, that's the relative density of gas in comparing it to air. Air equals 1. All these air and waters are on this sheet too. So I'm not pulling them out of my head, but they're 1. So air is 1, same thing. If it's greater than 1, it's going to sink in air. If it's less than 1, it's going to rise in air. And it's basically based on the temperature and its normal state of each chemical, of why we give different things. You also may see vapor pressure. You're not going to have to worry about that. There's a big calculation for calculating vapor pressure into vapor density, and I'm not going to get into that. So then you have your melting point and your freezing point. Melting point, obviously, for solids. Freezing point for liquids. Okay. And then your UEL and LEL. We're going to talk extensively about those. UEL is upper explosive limit. LEL is lower explosive limit. And then it's going to give a flammable class. And at the very beginning of your book is the flammable classes. And you don't really need to know too much about them, except for the chart at the front. On page XIV, if you guys turn to XIV, it tells you the temperature that the flash point has to be in order to be classified into the classes. Really, it means nothing for us other than if we see a combustible class 3A, we know that its flash point is more likely above 140 degrees.
I have a lot of question marks on all 4 of the rounds pages next to things, so, you know, with the UEL and stuff like that.
Yep.
So it's question mark, that means they don't know, or it changes?
If there's a question mark, they don't know. Or they can't reach that point. The chemical. They have not found a point at which they can reach that point. Okay. Same with, up in our IDLH, you may see a CA for cancer, and then it'll have brackets for how many parts per million they think it'll cause cancer at. Or it'll have an ND, not determined. So it might be toxic, but we don't know. Stay away from it. To the left of that box, is everybody clear on what the chemical and physical properties box does for us? Probably our most important box when we're talking about monitoring. Okay. The next one to the right of that is our personal protection sanitation. And then it goes through and tells you what you do for your eyes, what you do with skin exposure, when we have to remove our clothing, our PPE, and then what we have to provide for these victims. Beyond that, to the right is respirator recommendations, and that's more for the tech level. That's where we have to say, yeah, it's a 50 micron filter we have to use or whatever. So if we go down below chemical and physical properties and the 3 big boxes there, we got incompatibilities and reactives. In there, we're going to talk about, is it reactive to water? Does it polymerize when it touches air? Is it reactive to this chemical or that chemical? So it's saying, yeah, it's going to create some nasty stuff if it's mixed with water, or it's going to create some nasty stuff if it's mixed with air. Below that is your exposure routes, symptoms, and target organs. And ER is exposure routes, SY is symptoms, TO is target organs. And that's basically all that health stuff there. Now this methyl ethyl nasty stuff is going to do this to this organ and what you can do for it. And then to the right of that is first aid. Any questions on how to read a NIOSH? Because we're going to use that a lot. Alright, so let's get into our monitors now and talk about what sensors we have. The first one we're going to talk about is combustible gas sensors. This is the one that's probably going to confuse you the most. So I'm going to go real slow through this one. It's very simple. It's going to tell us whether something is at its explosive limit or not. Okay? And it's going to give us that information in percent LEL. This is basically different names for that sensor. They go by combustible gas sensors, flammable gas sensors, catalytic bead sensors, or catalytic sensors. And the catalytic bead and catalytic sensors are basically just how it works. We'll talk a little bit about that. They detect the flammability of gases. Exposure to a gas, a flammable gas, causes the bead to heat up. And then a circuit called a Wheatstone bridge compares the known resistance of a gas to the unknown gas and tells you whether it's flammable in air or not. So basically, gas comes in, Wheatstone bridge says, I know what this gas is at its lower explosive limit, and I don't know what this one is. Is it higher or lower? And it says this one's higher. So then we have to go in depth and figure out how much higher and why it's higher. Gives a percent reading, and it requires oxygen to aid in combustion. That's why if our oxygen sensor isn't working properly, if we're getting a false reading on our oxygen sensor, or if we're below that 19.5 or above that 23.5, we know that our LEL monitor might be off a little bit. If it's below that, we don't have enough oxygen to sustain combustion. If it's above that, we have too much oxygen. And then it could be even more flammable for us. So as we're using our monitors, we're not just looking, if we're looking for something on our LEL, we're not just looking at our LEL, we're looking at all the other placements on the monitor as well. The oxygen, the CO, that kind of thing. Here's what an LEL sensor looks like on the inside. It's calibrated to a specific gas. In our case, it's methane. And the reason that it's methane is because methane has a very small window of lower explosivity, and it's less likely to be fooled by gases. It's pretty specific. And then once we're going to talk about correction factors here in a little bit, but each maker of our monitors, in fact, MSA and Ray Systems, they both have different sheets, and their numbers are different. So if you're using the Ray Systems monitor, which is the new one, use the Ray Systems sheet. And I printed out the sheets for you guys today, so you'll have those in here if you picked them up. And then if you're using the MSA, use the MSA sheet. That's very important because they do their own tests on their sensors, and some of their catalytic beads heat up quicker than others, so their correction factors may be different. We're going to talk about terminology first. If we look at our NIOSH guide, and we look specifically to LEL, we find LEL as a percent. So if we go to propane in our books, alphabetically, propane, turn now, propane.
You didn't say this was hand
Definitely in. Don, tell me what the LEL of propane is.
2.1.
2.1%. 2.1% by volume. If you can remember, when you look in the NIOSH guide and you look at the LEL, if you add by volume, you're less likely to get confused. Okay, so 2.1% by volume. So that means if 2.1% of this air in this room were propane, it would be combustible, or it would sustain ignition.
It would be a lower explosive.
And it's a lower explosive level. Okay? Is 2.1% what we're going to see on our monitor? No. That's where I don't want you to get confused. So the NIOSH guide lists the LEL as a percent by volume. Try and remember that. Aaron, do you have a question?
I'd like to launch at 10% of the LEL.
Okay, we're going to talk about that next. So our MSA or Ray Systems monitor is 10% of the LEL. Of methane, not of propane. And that's why we have to use correction factors. Is everybody clear on that? Alright. Try not to get confused, because we're going to work through one. So our monitors are calibrated to methane. We talked about that already. In order to understand what our monitors are looking for, we have to understand methane a little bit, don't we? Methane's LEL is 5% by volume. So if you looked up methane in the NIOSH guide, I don't think it's in there, but if you did, it'd say 5% LEL. We also have to know that 1% of LEL that we find in our NIOSH guide equals 10,000 parts per million. So 1% of the LEL in our NIOSH guide is 10,000 parts per million. That doesn't mean if our monitor is reading 10%, we multiply that by 10,000. That's a totally different percentage. So our methane LEL is 50,000 parts per million. So if there were 1 million bubbles in this room of everything, and 50,000 of those were methane, we'd be at our lower explosive limit. Okay? Our monitors, however, alarm at 5,000 parts per million, or 10% of methane's LEL. Okay? Gives us a 90% safety factor due to correction factors Some might be more volatile than others. Some might be more reactive in air than others. And it also has to do with atmospheric differences. That's why we take them outside, to make sure that our temperature and humidity is right. So if we look at methane, if we're above our ULEL, we're too rich. If we're below our LEL, we're too lean. And if we're in between, it burns free and it's happy.
But at any point, if you UEL and you're too rich, you're gonna have to come down through your burn zone to get to your LEL.
Exactly. So if we were at 16% by volume of methane in this room right now, if we ventilated it out, eventually we're going to have to pass through 15%, 14, 13, all the way down to 5%. Okay? Our monitor is going to alarm at 10% of the LEL. So there it shows you in parts per million. Okay? We're going to talk about correction factors. So there's 2 correction factor worksheets, or sheets on your desk in front of you. One has black lines through some things, and one says PID correction factors. Set the PID correction factors one aside. We're not going to use that yet. We're just looking at the LEL correction factors. You're going to all ask yourselves why there's a black line through the percent LEL by volume. It's because these sheets are different than the NIOSH guide. And it's based on what Ray Systems says they are. Now, yes, we are using Ray Systems monitors, but the national standard is the NIOSH guide, so that's why I want you to use the NIOSH guide and not get confused. So we're actually going to use the correction factors column, but not the percent by volume column. Okay? Those numbers that you see there, those correction factors, are generated by the manufacturers based on laboratory tests. They're undisputed within that manufacturer. Now, MSA and Ray's numbers, as I said before, are all completely different. They run their own tests on different sensors. They may even have a different manufacturing facility. So they need to make sure that they are giving you accurate correction factors. Those correction factors enable users to quantify a large number of chemicals using only a single gas, which is methane. So basically, every time you go into a lower explosive atmosphere, it's saying, I got this much of methane, and it starts alarming. You see an acetylene tank over there, and you know it's acetylene, but your monitor is telling me, yes, I got something flammable in here, and I'm comparing it to methane, and I think it's methane. So then the correction factor takes it and changes it from methane to looking now at acetylene, and we're going to work through that so you guys don't get too confused. So our monitors can be calibrated, and we can use correction factors within our monitors 3 different ways. First way, we can calibrate with methane, and we can go into our monitor, it has a library in it, and we can change our monitor to look for that acetylene tank that we see sitting over there, or that propane tank that we see sitting over there. It does the math, and it gives the LEL as correct.
So when we start that MSA up, it says methane?
Yes. So we can calibrate to methane, and we can call it from the library, and it switches automatically. Or we can calibrate to methane and input a corrected span gas. That's all way too technical for you guys. The way we're going to use, and what I'm going to show you today, is we're going to calibrate to methane, which we do already, and then we're going to multiply the reading by a correction factor to figure out the percent of the LEL. Okay. So, propane we know is correction factor 1.6, right? We look on our chart, our LEL correction chart, 1.6. If our monitor, we go down range and our monitor reads 10% of the LEL, what's 10% mean to you guys?
10% of methane.
Of methane, right? 10% of the LEL. Is this the number that we're going to see in the NIOSH guide? No, because that's by volume, right? That's its actual lower explosive limit. What we see on the monitor is a percentage of the lower explosive limit, okay? And we use that because of these correction factors may bring some chemicals higher and some chemicals lower. So we take the 10%. If you can ignore the percent sign on your monitor, that's always good too. You won't get confused. just know that it's 10. You take your 10 times 1.6, you're now at 16% of the LEL of propane. So when you're at 10% of methanes, you're at 16% of propanes.
So it should be alarming then.
It should be alarming. It'll alarm at 10% of methane. It doesn't even know it's propane.
Right.
You've got to know that it's propane. And that's where looking at containers, vessels, that kind of thing, when you get on site, is going to say, hey, we don't have anything else in this room, but I've got a propane bottle over there that's venting. Okay?
So acetylene, which is a 2.8,
We'll go through all that. We'll go
there's
through all that.
28%.
So everybody clear on that? Don't multiply the correction factor by 0.10. So don't use this as a percent, use it as 10.
So
that clear?
0.9 means it hasn't technically reached it yet of the chemical when you do the correction factor if you have one of 0.9.
Correct.
No, it would just be 9.
9%. So it wouldn't,
It would be 9%.
so
Right.
it wouldn't have. met.
Correct. Correct. Clear? Clear as mud? How you doing with this, Karen? Clear? So we know that LEL to parts per million. We've got to calculate that because some things are more toxic at levels than they are flammable. And some things are more flammable at levels than they are toxic. And the only way we're going to know that is if we break everything down to parts per million. Break the room down into a million little bubbles. Tell me how many bubbles I have, then I can tell you how toxic it is and whether it's flammable or not at this point. Okay? So LEL to parts per million, we know that, I told you earlier, 1% of the LEL in your NIOSH guide is equal to 10,000 parts per million.
For just methane?
Nope, for anything. For anything. That's a given. We know that 1% of LEL is equal to 10,000 parts per million. So then we go 10,000 parts per million times the LEL by volume in our NIOSH guide. Okay? So if it has a what was propane, 2.1?
Propane was
Yes.
1.6.
1.6.
1.6.
16%.
No, you're talking correction factors, I'm talking LELs now.
Oh.
So your
Blacked
LEL
out.
propane,
You blacked it out in there.
yeah, go to your NIOSH guide.
Here it is,
It's
2.1.
2.1.
2.1.
2.1 times 10,000, 21,000, right? So the lower explosive limit of propane we know now is 21,000. Pretty simple math there, right? 1% of LEL equals 10,000 parts per million. Look at your LEL in your NIOSH guide, 2.1 times 10,000, 21,000 parts per million. All right? LEL parts per million times 10%, or 0.10, equals 10% the LEL parts per million. That calculation you don't have to worry about so much.
So it's 2,100.
So it's 2,100. Okay? So propane, if we break it down, 2.1% times 10,000, 21,000 parts per million. 10% of the LEL propane is 2,100 parts per
So it's going to alarm at 2,100 first. Right?
million. No, because that's propane.
Oh, this is the methane.
You're calibrated to methane, so don't get confused. So if the monitor reads 10% the LEL, then there is 16% of the LEL propane, or 3,360 parts per million of propane. So 21,000, we take our propane parts per million, because we broke that down now, we're multiplying it by 0.16, you're going to get 3,360. So propane's venting into this room,
Got it.
million bubbles. 3,360 of those bubbles are now propane. Are we at our LEL?
330, 360.
Are we at our LEL? What's our LEL
You're not
propane?
at your LEL, you're at the alarm. You're at 10% of your
You're at 10% of the LEL, but you're not even at the alarm yet on methane because it's, you see what I'm saying? Because it's only 3,360.
The alarm methane's 2,100.
The alarm on methane,
2,100 because it's a higher factor.
is 5,000. Who's confused?
Just a lot of math.
It's a lot of math.
Well, you have a
You guys got it?
hazmat branch.
Alright.
Hazmat group.
So let's do a settling. Look up the settling in your books. Your first practice sheet for LEL calculation is a settling.
Got a sheet right there.
So answer your questions. Don't move on to gasoline yet, but just do a settling. So your sheet should look like this. Those should be your answers for a settling.
But how, tell me how you got 7,000 again.
Yeah, I got 10,000.
What did you do?
Remember, your monitor's reading 10%. So you know that your LEL in that room, your percent of the LEL is 28%. So 0.28 times 25,000 gives you how many parts per million are in that room right
You
now.
said 0.28, right?
Yep. Yes.
Don't ask me how it goes.
Because 1% of your LEL is
10,000. Did you get it? What are you having trouble with? You've been through this before, man.
I know, I heard.
I just wanna,
You
so
got it right?
settling is flammable, 10% of methane.
No.
No.
Yeah, it is, because it's 7,000 versus 5.
It was that part that we're talking about, that 90%. This
Right.
is just to tell you something's in there.
But it's,
This is the LEL of acetylene,
Right.
based off this number you found in the NIOSH. So are we there yet? We're not even close. We've still got a lot of growing to do here to get to this number
But 5,000
But that
parts
just
per
gets you
million
to-
was
yeah.
what the LEL is.
of methane.
Methane, that's where I got it.
And you gotta forget those numbers now that you know you've got acetylene in the room. Once you know that you've got acetylene in the room, the only thing you have to remember is that that number on your monitor correlates to the correction factor, gives me my percent of the new gas, of the LEL.
Methane's just telling you you got a problem. Now you
Yes.
gotta find out what is the problem.
Exactly.
How'd you get your 28% of the LEL? How'd you get that
He
one?
brought it from number 2.
Yep.
Correction factor.
Your correction factor times 10, or your correction factor times 10 equals 28%.
Right.
2.8 times 10, 28%.
So you actually
28% goes down here.
Last two.
Becomes 7,000 parts per million. Then you compare it to this number.
Because you go 0.28 times 25,000, you get 7,000.
Yes.
What was everything?
0.28,
7%.
because it's 28%, right? And when we do math with percentages, it's point.
Yep.
So 28%
Which one?
times 25,000
Wow.
should make 7,000.
It shouldn't allow.
Get an alarm.
So I walk in this room, my monitor alarms 10% of methane. I take my correction factor, 10 times 2.8. If it was 20 on here, I'd multiply 20 times 2.8.
Same thing with walking in with a lighter.
Exactly.
Same thing with walking in a lighter. You've got, well, it's 28 before you get to basically the 100 thing, but that 90% correction factor, you can keep that lighter lit
Yep.
up until it reaches 100.
25,000
Right.
parts per million in that room. You're not going to know how many parts per million are, but this helps you calculate how many parts per million.
You've still got those two questions
Yep.
on there.
So our two questions are, is it flammable right now? Is it at its lower explosive limit?
No.
If you get right up to the nozzle or where it's leaking,
Maybe.
probably.
Or by then it could be too rich, too.
Or it could, well, you'll find out acetylene's never too rich. I'll show you here in just a minute. So 7,000 is less than this number, and this number is, we know the magic number based on this number that's in our NIOSH guide for acetylene. 25,000 of these bubbles in this million bubble room have to be acetylene for us to walk in with a lighter and it go boom.
Do you have one of these for the other monitor?
Yes, they're in the case. Still tracking?
Remember, there would still be like a research team that would be
Yes.
sitting somewhere.
I just want you
with
to
the radio.
be able to think about why we're getting these numbers and what we do with this information.
So it also asks, is it toxic at 10% methane?
Where are we finding if it's toxic or not? In our NIOSH guide. What's the box that tells us it's immediately dangerous to life and health?
Not determined. It says ND if you're looking at
Not determined.
IDLH.
So, if we breathed in acetylene, what's our worst fear? Is it did it displace all of our oxygen or not, right? Okay. So let's break it down. Look at these right here. He's going too slow. So this top box is methane. Okay, we've got it broken down into 10 big orange block boxes. Down here on this end, 0%. Up here on this end, 100%. From our book, we know methane, from what I told you, we know methane's at 5%, the LEL. So way down here, if we've got 5% of this room is methane, we're at our LEL. 15% is the UEL of methane. So we've got this narrow window that we could figure out. This is our 50,000, because it's 5%. 1% equals 10,000, so at 50,000 parts per million, we're here. Bang. Our monitor is going to measure it here at 0.5%. It's going to say 10% of 5% by volume is 5,000. And that's where our monitor is going to alarm. So we've got this whole space.
Which is a lot. When you look at that graph, it might not look like a lot, but it's a lot.
It's a lot for methane, okay? So there's methane. Our alarm goes off here. Here's acetylene. Acetylene doesn't have an upper explosive limit if we looked. So as soon as methane reaches 2.5% in air by volume, it's always flammable. That's why when you light your acetylene torch without the oxygen turned on, it's going to burn immediately. That's why when you add the oxygen to your acetylene torch, it's going to burn even more intense. Because it's from 2.5% by volume to 100% that it burns, okay? Or a UEL. So then, it'd be 0.25%, you don't have to know this, but it'd be 0.25% if you were looking for 10% of the LEL here. But 25,000. So are we still below our LEL of methane at 25,000? We are, because methane's LEL is 50,000. Okay? And we're still below our percent, your 10% methane at 2.5%. And that's why we use methane. Okay? Does that help describe it a little bit better? Or did that confuse you?
That one didn't, no.
Okay.
That one didn't help.
No.
But I got it before.
This is the flammability range. This is the flammability range. Our monitor is going to tell us here, well before we're even close to our flammability range. And then we use our correction factors to figure out where we're at. All right, let's move on to gasoline. So remember, get our LEL of gasoline from our NIOSH guide, get our correction factor from our correction worksheet, and we still walked into this room and got 10% on our monitor. We're still using that number because it's easy math. Okay? I mean, I could have been a real dog.
So is acetylene toxic at 10% methane?
What's it say? Up in your IDLH, because that's the one we look at to determine whether it's immediately
Like a
dangerous.
frostbite,
Yeah.
basically.
Not determined.
Not determined.
But you could
Do we have any RELs or STELs or PELs or RELs or TWAs?
RAL.
So yeah, so it's, REL, so 2,500.
2,500. So that's what they're saying that you can be exposed to in a 10-hour workday over 40-hour work
So
week.
there is some
Is
toxicity.
that the last question?
Very little. Very little.
That's actually-
Compared to your LEL, is it toxic though?
No.
Or are you going to burn first?
See?
He's toxic.
it's toxic, but it's not toxic to the point that our worst fear with acetylene is burning up, not killing us right now. At what % can we affect a rescue in a flammable atmosphere?
90%.
No, probably not that.
What
50?
percent of LEL is that what you're talking
Yes.
about?
50?
At what % of LEL? Depends on if it's enclosed or non-enclosed.
I would
Oh,
assume
I mean, I don't know.
10%.
10%
You say that first.
compression factor.
Outdoors, 25% of the LEL.
Indoors.
Yeah.
Indoors, 10%.
What it is, right?
So right when you're alarming, unless you hit
It's
your correction
2100,
factor there.
Now, knowing what you know of acetylene, if it was free burning and there was somebody laying there, the bottle fell over on them, could we do it at 28%? Yeah.
Well, you can do a breathing apparatus and.
You're well below your 7,000 parts per million at 28% on your lung. $29.40 of this number that you find, less than that, you're not flammable, because you're not there yet, right? That's why we have the 90% correction factor.
How do you determine that it's toxic, other than you just look at that? and
You look at this, and you look at this. And if it's got rel, stels, pels, TWAs, then it's got some toxicity. Now you gotta figure out, is my number that I came up with here above any of those? Any of the numbers that we listed here.
Oh, so if there is nothing, I guess.
Yep. So if you look at,
That's like that.
yeah,
Right.
so it's not determined at any level that it's toxic right now. It's not gonna drop you to the floor. You go into a room, we know, we pump gas all the time.
Right.
We're not dying, we're not falling over death, right? The big box that we need to remember if we wanna figure out if it's toxic is IDLH. It's immediately dangerous to life and health. That means if I walk into this atmosphere of gasoline, bam, I'm out. Just like the guy on the show with ammonia, right? Guy walks up, immediately dangerous to life and health, he's down. Okay, that's the box that we have to know about for toxicity. And then if there's nothing there, we just keep in the back of our mind, I can also look over here under my relative exposure limits, my time-weighted allowance, and that kind of thing. The things that the government says, okay, yeah, it's toxic, but we want you to only work in this atmosphere for this long. Okay? Alright, ammonia, LEL, 15%. That's way up there, isn't it?
Yeah.
That's why they were able to talk to Congress and get that flammability placard taken off of their anhydrous ammonia tanks out in the fields. Because it's way up there, 15%. So 150,000 is what we get after we multiply 1% times, or 15% times 10,000. 150,000 parts per million is its lower explosive limit. That's when, if 150,000 of those micro bubbles in this million bubble room is ammonia, we're going to be able to burn. Okay. Correction factor of 0.8 gives us 8%. So I'm walking down range. My LEL monitor goes off. Actually, two are going to go off, but we're going with LEL. LEL monitor is going to go off. Gives me 10. I see ammonia, I back out. I go back, I figure out my correction factor is 0.8, 8%. So when I was at 10% of methane, I was actually at 8% of ammonia. So I'm low, right? It makes sense. Methane's 5%, ammonia's 15%. Okay, it makes sense. So then we take that 8% and we multiply it by 0.8, or with that 0.8 times the LEL of ammonia we know is 150,000, we come up with 12,000 parts per million. So our questions then are, is it flammable?
Yeah.
At 10% of methane, is it flammable?
No.
Did this number meet that number or greater?
0.8 times
Anything above 1 point
Yes.
is a yes. What did you do?
Isn't it 0.2 Yeah, point zero.
Point zero eight.
This is times that by 10.
0.08. Remember,
We've always done that.
when calculating percentage,
Then 8%.
tens column, hundreds column,
You gotta add that 0 to make that 8.
0.08.
0.08. That's
0.8 would be 80%.
8.
Yes. And even at 80%, we're still not there yet, at 120,000. So then the next question is it toxic? What is ammonia gonna do to us if we walk into the room? Is it gonna blow up on us first, or is it gonna knock us out right now, immediately dangerous to life and health?
Knock you out.
What's the IDLH?
300.
300. Huh. We're dead if we walk in there and we look at only our LEL monitor at 10%. We're dead if we're not an SCBA. Just like the cop. So see how that becomes important? Looking at LEL, looking at parts per million, why we break things down into that to figure out what our monitor is actually telling us.
Not long ago, in an ore mine, a drill struck a water course.
1960s.
When water, under pressure, was released into the drift, work had to be halted. The next day, a miner went in to inspect the water flow. Hydrogen sulfide gas. Its immediate effects are eye irritation and tightness in the chest, and it has an odor of rotten eggs. But under high concentration, this is not detectable, for the sense of smell is quickly paralyzed. The condition was reported, but adequate precautions were not taken. Over the weekend, one of the fans failed, allowing an accumulation of the gas to build up. Monday morning, while it was being repaired, a miner entered the drift to recover a tool. He never returned. A half hour later, two other miners went in after him. When neither of them returned, another miner entered, and before it was over, 3 more had died, bringing the toll to 7.
Electrochemical sensors. They're specific sensors. They're not like our combustible gas sensor in that they look at methane and say if something in here is going to burn based on what we know methane is going to burn, but it's actually specific. There's a ton of them out there. We could put 150 different ones into our monitors. But in our monitors, we have the oxygen, obviously, the ClH2S, and the hydrogen cyanide is in the ray systems. They're a chemical mixture sealed in a sensor housing. Gas passes over the sensor, causing a chemical reaction, and it's an electrical charge is created, and microchip processes the differences. Porous measuring electrode here. The gas comes in through the diffusing membrane, mixes with this electrolyte. Inside the electrolyte, some voodoo magic happens, and it splits it, sends one part to this reference and one to the counter, and then same thing, it compares the difference between the two. And the bottom actually tells you, but that's all voodoo magic, you don't need to know any of that. What sensors do we have? We got oxygen. It's measured in percentage. It measures from 0 to 30%, and its low alarm is 19.5, and its high alarm is 23. Carbon monoxide, measured in parts per million. There's the IDLH, so we know there's no conversion here. If it says 35, it is 35 parts per million. If it's 100, it's 100. It's got a low alarm at 35 and a high alarm at 100. Hydrogen sulfide, which we saw in the video. Hydrogen sulfide is actually a gas that's made from the decomposition of organic material in water. So that's why we had that rescue not too long ago up there in the trailer park. or near the trailer park where the guys went into the sewer, it was hydrogen sulfide gas that took them out. The video pointed out pretty good key too is that your olfactory sense is paralyzed pretty quick. It's measured in parts per million. IDLH is 100 parts per million. It's pretty low. So our alarms are even lower at 10 parts per million, 15 parts per million. And then in the multi-ray, we have the ability to detect hydrogen cyanide. If you compare the IDLH of hydrogen cyanide with hydrogen sulfide, it's even lower yet, 50 parts per million. So our low alarm is 4.7, and our high alarm is 75. Pretty simple. The monitor is going to tell you, I have CO, I have it at 35 parts per million, it's going to alarm. Okay? There's no correction factors involved, it's straight up. Photoionization, or volatile organic compounds, you'll see it as VOC on the monitors. Technology uses an ultraviolet lamp, basically shoots light across the spectrum. Particles are then ionized, turned into both negative and positive charge. Gases that are sampled must have an ionization potential. That's that IP that we're going to find in our NIOSH guide. We talked about IP already. Ryan, what's it have to be below if we can detect it?
Oh, 10.6.
10.6. It's specifically measure parts per million of gas to determine IDLH and correct entry ensemble. Reads as parts per million in the monitors that you'll be using, and in the one ray system monitor in parts per billion. It's more sensitive, in other words. This one's on 417, it reads in parts per billion. It'll actually switch back and forth. As it hits its parts per million limits, it'll go to parts per billion. Parts per billion is more sensitive. So this is how it works. Vapor enters. The bulb fires, splits it, sends the negative or the positives away. The negatives it reads, collects it, and amplifies it, does some more voodoo magic, and comes out as a parts per million or parts per billion reading on your VOC. And then the vapor exits, reforms, essentially unchanged, to become toxic. So anything that has an ionization energy less than the bulb, our bulb is 10.6. We know where to find that now on our NIOSH guide. Uses a standard calibration gas, which is isobutylene. Isobutylene is a simple asphyxiant. It's going to displace oxygen. Okay. There's its chemical, its chemical. I can't think of it right now, but the C's and H's and all that. And it's calibrated at 100 parts per million.
Chemical formula.
Chemical formula. That's what I was looking at. Chemical formula. And then we compare the PID correction factors to isobutylene. And again, the correction factor worksheets that you guys have in front of you, the correction factors for the PID, it's for the multi-ray. The MSA has a completely separate sheet. Again, there are three methods. You can calibrate it with the PID with isobutylene. You can call it the sample gas from the library by changing some buttons. Calibrate it with isobutylene, and you can manually enter a corrected span gas calibration concentration. Or you can calibrate with isobutylene and manually multiply the parts per million reading. Okay? What does it measure? Organics. What are organics? There is a whole ton of them. Pretty much though, anything in its chemical formula with a C, or with carbon, is an organic. Okay, so aromatics, ketones, methyl ethyl ketone, amines, chlorinated hydrocarbons, your gases, that kind of thing. Sulfur compounds, mercaptan. So if we're in a natural gas environment, the natural gas won't show up, but the mercaptan will. If you look up mercaptan, it's got IDLH levels as well. Unsaturated hydrocarbons, alcohols, your ethanols, methanols, saturated hydrocarbons, and inorganics like ammonia and arsine. And that's where, if we go down range, what's going to alarm first on our ammonia? Just knowing about what we talked about on our monitors right now, Aaron. Is it gonna alarm for VOC or is it gonna alarm for LEO? What's lower?
LEO.
What's lower? Is your IDLH for ammonia or is
Oh, it's gonna alarm on the,
on the VOC, right?
Yeah,
Because the alarm limits for VOC is 100.
right.
And 100 parts per million of ammonia is gonna kill you right now, but it's not flammable yet.
Correct.
Okay? That's why we look at all of our monitors, all of our sensors. What don't they measure? Radiation. It's not going to tell us if the neutron bomb went off. Air. It doesn't measure nitrogen or oxygen. That's what we have our other sensors in there for. Toxics. Carbon monoxide, hydrogen cyanide. That's why we have those sensors. Natural gas, it doesn't actually measure for methane or ethane. The VOC doesn't. But remember, that's where our LEL will measure those flammable gases, like natural gas. Doesn't measure acids, and acids in particular are nasty with our monitors. Between acids and fluorines, those are the ones that are going to get us in trouble the most. And I'm just going to pause for a second here and tell you that acids, that's why we wear our pH paper if we're going down range. Acids will destroy the monitors. They're going to tear up your oxygen sensor, your LEL sensor. If you have acid vapor, they're going to react with those. That's why we have our pH, because as soon as that turns a different color, whether it be alkaline or an acid, it's going to be nasty stuff for our monitors, and we back out and we come in without our monitors. And then our fluorines. And the reason the fluorines are so nasty is that they react with the sweat, and just a small amount of sweat on your skin will send that fluorine looking for calcium in your bones, and it will kill you right now. So that's why we wear our K paper and our fluorine paper.
It says others, it says freon, ozone.
Yep.
Ozone's oxygen.
Well, yeah, at high levels.
So
That's what ozone is. So
it does read that.
your monitor reads oxygen, but your VOC monitor does not read oxygen. Okay? So our correction factor exercise, let's pull out our worksheet and work through that. It's pretty self-explanatory. So you take and figure out all your information from your NIOSH guide, put it down on your worksheet. The only thing that you're going to use is your correction factor worksheet. And on this correction factor worksheet, before we get too far into it, it's got your compound name at the top, synonyms, trade names, your CAS number, formula. Then it has a 9.8. That's for a 9.8 bulb. Your correction of plus or minus. And then your 10.6 bulb and a correction of plus or minus. So the number that you're looking at for your correction factor for your PID
10.6.
is the 10.6. Okay? And at least for the multi-ray ones, this is actually in the case. This is the one that you're going to compare it to. And it's laid out the same as your worksheet or your correction factor sheet. This is your correction factor for your PID only. So then we're comparing that correction factor to 100 parts per million of isobutylene. So you're going to take your correction factor, multiply by 100, because that's where it's going to alarm, is at 100 of the VOC, and that's what your new parts per million is for the chemical that you may be monitoring for. So for toluene, what's our correction factor?
0.50.
So our corrected, if we're showing 100 parts per million and our VOC is alarming, what's our corrected amount in parts per million for toluene? 50. So that one's actually more toxic than isobutylene is telling us. It's not even going to alarm. It'll alarm for isobutylene, but saying that there's a toxic there, but it's not going to. It's going to be well over its parts per million. How do you figure out if it's flammable? So 50 parts per million. Now you look at the LEL of toluene. 1.1 times 10,000.
Is this flammable when wet?
11,000. Your VOC alarmed at 100. Your correction factor times 100. You walk into this room, 100. You see the thing of toluene over there that's spilled on the ground. I go back. My monitor alarms at 100. I go back. I look up my correction factor, and I find that it's 0.5. When I go in and my monitor alarms at 100, I know that it's at 50 parts per million of toluene. And now with that information, we can answer the rest of our questions. We can figure out our LEL, because 1% of the LEL is 10,000. The LEL of toluene is 1.1, so 11,000 is our LEL. We've got 50 parts per million on our monitor. We got 100 on our monitor. We know that it's 50 with the correction factor. Are we at our LEL yet? No. We're not at our LEL. Are we toxic? We got to go back to our IDLH box, right?
Our IDLH is 500.
So we're not yet toxic. So we're safe. Now, Ryan, can you tell me, is this going to rise in air or float on air? Or rise in air or sink in air?
I think it's gonna rise. What's our, is it 1? We're at point, specific gravity is 0.87.
Molecular weight, 29. Is it bigger than 29?
Oh, yeah.
Okay. How about water?
Not that, no.
Is it gonna rise to the top like oil, or is it gonna sink, or is it gonna mix? We're looking at specific gravity there, right? And molecular weight, we calculate that as scientists by figuring out how many protons, neutrons, electrons there are. And that gives us our specific molecular weight. So we're working on ethylene oxide. The only thing you really have to memorize is that 1% LEL equals 10,000.
So you take your 30,000 and what can you times that by your
Nothing for ppms.
okay.
All you're doing
Well,
is you're comparing your 30,000 that you get for your LEL to this number.
Oh, okay.
And if this number ends up being higher than 30,000, you're at your explosive limit.
Okay.
Your lower explosive limit.
Oh, you said 30,000?
3.0 times 10,000.
Yeah, got it.
All right, so is it heavier than air or lighter than air?
It is lighter than
Heavier
air. Oh, I'm sorry, that 29, so it's heavier than
Heavier than air, but it's
Molecular weight.
Water, it's gonna
Molecular
float
weight
on
is reference to air,
water. Right, it's gonna float on water though.
but it's going to float on water, right? Because that's specific gravity. All right, ammonia. Should be pretty close to ammonia here. We've talked about ammonia all day. This number here is how much ammonia you have. In this million bubble room, you've got 970 of those bubbles are ammonia. If you had 150,000 of those bubbles, it'd be flammable.
Ah.
Correct. So what's our hazard with ammonia? One lesson that we could learn today.
Toxic?
Ideally.
Ideal H, it's toxicity, right? It's gonna kill us right now versus go boom on us right now. Now can it? Does it have the potential to go boom on us? Absolutely. If we're in SCBA and turnout gear, is our chance of getting hurt lessened? Absolutely. Are we gonna be killed right now if we're in SCBA and turnout gear?
No.
No, because our gear's gonna protect us. You guys see why they put water on that plume at the beginning? Because it's mixable with water. And so what's water do in air? Turns its molecular weight, drops it to the ground.
Absorbs in the soil so they can dig it up with an excavator later.
If they even need to. If it's near crops, they probably won't. That's pretty much it. I'm just going to show you now the actual specific monitors. But this information is going to help you when you go down range and you start to see your monitor do funny things. Alright, so let's talk about our Array Systems monitor. We have two. They're brand new. There's a yellow one and a black one. Unfortunately, when you take the yellow sleeve off of this one, it looks the same as if you take the black sleeve off of this one. So if you take the yellow sleeve off, make sure you don't put the yellow sleeve on the black sleeve.
So they're different monitors then?
They're absolutely different monitors. This one's going to measure in parts per million, which we've been talking about all day long. This is the one that's going on the truck. It's going to operate exactly the same or very similar to the MSA. It's going to alarm at 100 parts per million. It's going to alarm at 10% of the LEL. It's going to alarm at 35 parts per million of CO. Okay, so this one's going to be very familiar to you. The only difference with this one, they're exactly the same setup. Both have hydrogen cyanide monitors. The difference with this one, it's going to measure your VOCs in parts per billion. So it's going to be more sensitive.
That's the one that has that.
This is going in the hazmat unit, and you shouldn't have to worry about it.
Clear, truck 436.
So if we look at the front side, at the top we got the external filter intake. The white part there, you'll see in another slide that it actually unscrews. Everything that screws into that port at the top, whether it be your probes, your filters, they're all lure locked, so it just like our IV stuff, it screws right in, no problem. It's got an LED alarm lights at the top and the bottom. There's an LCD display, power button right in the center. There's a Y+ button, an N- button, rubber boot. The alarm buzzer, instead of, look on the MSA, the alarm buzzer is down here. The alarm buzzer on the multi-array is right in the center. So that, we've got to make sure that we protect that and we don't get any gunk in there. Okay.
What vehicle is that going on?
This one is going on 413, as soon as this class is done.
Do we have one on 436?
You will not. Not until we get more.
Just the old Cirrus MSA.
And Ken Van Hall wanted me to tell you that both of these are RRTN money monitors. So that one in specific, the one that's going to be on 417, has to stay on 417.
So even if one of ours is broke, we can't take it off 417 to put it on truck to use it?
No. So on the bottom you got a charging port, and on the top you've got a standard inlet and a replaceable inlet filter. I'll pass this around so you guys can kind of take a look at it. Don't power it on just yet though. The black boot, this also comes off, and you'll have to change that out if you're going to calibrate it by hand, so you guys won't have to worry about that. This area right here is the gamma source, but this isn't a gamma monitor, so we're not going to worry about that. And then your replaceable filter. We have several dozen of those, so we should be good. On the back side, you got a swivel removable belt clip. You remove it by taking out that Phillips screw, pull it off. There's a lithium-ion battery, battery retaining clip. As you look, you can just slide it up and down. The hex bolt rubber case retainers. I made the mistake of thinking it was like the MSA, and I pulled that rubber boot off, no problem, but then the hex bolts were left hanging there. Take the hex, if you're going to remove the rubber boot, take the hex bolts out first. I had to do some funny monkeying around to get them back into place.
What's the suggested life on the battery as far as like hours or?
I didn't get that in depth, but it's going to be easily 8 hours. Okay, that's typically what they are for those. There's what it looks like without the battery. It's labeled regen and fiscal year 20.
Do you have those chargers in the house?
We do. There'll be one put on the charging cart.
Not in the engines?
No. Charging cart. And then the base station charger. Looks like that. And you just slide it.
And that will charge both the yellow and the
Yes.
black ones.
So you have to be on the rubber boot to do that, slide it in there.
There is an alkaline battery pack. It's labeled alkaline. If anybody's seen the alkaline battery pack for the MSA, it works very similar to that. Fits in the same slot. You use the hex head and put AA batteries in it. That's your alkaline battery pack. There's that tool that's in the case as well to remove that boot. You guys shouldn't have to do that unless you have to decon it or something. So our power on screens, we're going to hold the power on. It's going to go through a self-test about 10 seconds. Gives you the information screen, tells you what it is. Now the difference when you power on the black cased one and the yellow cased one is this is the yellow one, it's going to say Lite, and the other one's going to say Pro.
The power on button is the middle one that says mode key in our little description here.
The big button with the, yes.
Big black one in the middle.
Yep. I got a picture of it up here too. It's going to give you the software, build date, that kind of thing. It's going to tell you which sensors are installed, and those are accurate for both of the monitors. So they have the Oxy, the LEL, the CO, the H2S, the VOC, and the hydrogen cyanide. We talked about all those already. 0 at start lasts about a minute. This is the one where you're rolling down the road, you hold the nozzle out the window, get it to 0. Don't abort it. It really screwed it up when I aborted it. So don't abort it. Always 0, let it go. Takes about a minute. Then it's going to ask you fresh air calibration. And that's the one where it's similar to the MSA where you have to hit 0 or not. You have to actually hit start or quit. That one, if you're not in a fresh environment, hit quit. It'll take the information from the last time you called it up. Start calibrates to current temp and humidity. Make sure all the sensors are working. It lasts another minute. So there you got about 2 minutes and 10 seconds. That one takes about a minute total. So it's a little bit longer wait time on the array systems. Abort continues without fresh air cal. So that's where if you knew you were walking off the truck in an atmosphere, you would abort that. Power up screen is going to tell you after your calibration comes in. It's going to tell you which ones passed, which ones failed. If any of them failed right now, you guys aren't calibrating. Just the techs are going to calibrate these. And we don't even have the right tubing and span gas yet to calibrate them. So they have been calibrated already, but we need to be supported yet. It's going to tell you what passed. It's going to give you your fresh air cal reading. With this one in particular, and the reason I tell you that we're not going to fire this up probably every day is that in order, when you fire this up, it's going to read in parts per billion, the one that's going to be on the TAC truck 417. If you fresh air calibrated it right now in this air, it would pick up parts per billion of whatever's in this room. Whereas the other one in parts per million won't pick up anything because there's nothing that big of that much quantity in this room right now. But this is going to pick up the nitrogen, everything that we normally breathe in and out on. So it's, when we fire it up and we fresh air calibrate it, this filter, this charcoal filter, has to be in place and on it. And then the rubber boot on the end has to be removed. Okay? Because otherwise it's going to give you a parts per billion reading. That's one of the reasons why we're not going to fire it up every day, because this has a lifespan. And probably the techs are going to do that on a periodic basis. Gives you your current readings, and then it goes right to your sampling screen. And that's what you're typically going to see when it's monitored. So from your sampling screen, it's going to tell you that the pump is working. There's a little icon that swivels. If it's not swiveling, the pump's not working, you can't hear the pump working, you've got a problem with your pump. There's a data logging icon. Right now it data logs everything. You won't have to worry about clearing out the data log like we used to have to on the FID. It simply replaces the old.
You download that stuff?
You can. If you have an incident, you can download it. There's a battery icon. Like I said, just charge it on its major. You shouldn't ever run out of battery. About an 8-hour window on that.
What if it says full on the major day? Should you charge it?
Yes. The alarm activation, that Y plus button from the sampling screen, that Y plus button causes it to go into alarm mode. So if you tripped and fell and you couldn't get out on your radio, you could hit that as alarm, and the alarm's inaudible, alarm automatically says that you're in trouble. There's the power button right in the center. Hit and hold, turn it on and turn it off. Scroll button gets you to different screens. For the engineers, on a daily basis, these are the cal, whether it's in cal or not in cal. Full bottle means it's calibrated and it's good to go. An empty bottle means that it has to be calibrated.
And that's showing empty?
That's full.
What's it look like if it's empty then?
It looks empty.
Like a battery
Yeah,
showing.
like a black. in the center there. It's pretty hard to, when you see it on the monitor, it'll also alarm that something is out of cal. Okay?
So you have to calibrate the whole thing even though one of those is off?
No, this one you can calibrate each sensor. But like I said, you guys won't have to worry about calibrating it. For the most part, I'll take care of it or vandal. At least until we work the bugs out of it. So if we scroll from that sampling screen, we use that arrow. This is the next one we get. It's peak readings for this time. So I powered up, I went down range, I got a peak reading of 35 parts per million on my CO. I come back out of range, it's zeroed down, I can go to this peak reading and it'll give me, you hit 35 parts per million in CO. Okay? Minimum readings. It's probably always going to be this unless you walked off the truck and you had readings, and then it'll read the minimums that it was. Or you go downrange, you get your peak readings at 35 parts per million CO, you come back out, you zero it out, you ventilate, you go back in, you get your normal readings of 0, it'll give the minimums there. Scroll again, scroll button, it's going to give you your short-term exposure limit readings. If it meets any of the short-term exposure limit that are programmed into the monitor, then it'll tell you to met those. And that's based on OSHA and NIOSH. Again, TWA ratings, again, it'll tell you that. Give you the date and time. That should be current. If it's not, let me know. And I'll change it. Temperature and humidity, so this will actually tell you what the temp is outside, how much humidity is in the air, and that is another visual key to say, hey, I'm all set up and ready to go for this temp and humidity. Battery type, it's the lithium ion. If it was alkaline, it'd say alkaline. How much voltage and how much till it shuts down. Run times, how long it's run this time and how long it ran the last time. Gives you your VOC status, so again, we're still scrolling with that arrow, with this N+ button, or N- button. We're still scrolling. So this is from that sampling screen. Every time you hit it, I snap a picture. Gives you your calibration gas and its correction factor. We know isobutylene is the gas that it's measured by at 100 parts per million, so its correction factor is obviously 1.
So this is isobutylene and not methane?
This is for the PID.
The VOC.
Oh, okay.
VOC.
Okay, got it.
Okay? It's going to give you your LEL gas next,
Got it.
so that's methane. And it's going to ask you to enter communications mode. Don't. Some added features of the multi-ray, it's a flip screen like your smartphone. If you turn it on, you can flip it upside down, the screen will flip. It does not go sideways, it goes up and down only. It's got a calibration status symbol, which we talked about. If the bottle's full, it's cal's good. If the bottle's empty, the cal needs to be done, and it'll alarm at you. And then it'll illuminate. And if it doesn't illuminate at you, you can just press the power button in the center and it'll illuminate. Any questions about the MS or the Ray systems? All right, we're gonna go talking about the MSA next because I think it's a good overview. So our MSA is this one. The Ray system's the yellow booted one or the black booted one. This one you guys should all be familiar with, but there's a couple things I want to talk about here. The LED alarm lights, PID bulb access, that you should never open. That's that right there. Your power accept button, page button, reset button. It's got an LCD display, and it's got the audible alarm cover. From the bottom, you can see the audible alarm cover. I've got one on order for one of them. There's one that's broken. The D-ring in case you want to put a wrist strap on it. Part number, serial number, manufacturing date. For the engineers or for anybody who writes one of these up, I've got an Excel spreadsheet on my laptop that I have all of the maintenance that I've done for all of the monitors up to this point. If you can give me that serial number, meaning the A37448 on this particular one, if you give that to me when you say, hey, this monitor's not working, I've taken it out of service, I put it on the cart, I can look up and see, yeah, I need a CO sensor on that already, or I can look up and say, maybe you're having a problem with the alarm. Well, I can look up and see that I, change the alarm limits or whatever. Okay, so if you can give me that number, that'd be helpful. When Bob Lane breaks it, I'll know I'll know a little bit ahead of time what I need for it. The A09 on that is also the data manufacturer, in case you want to know the MSA. For the array system, it tells you what the data manufacturer is. The A09 is A is 1 for January, 09 is year 2009. Battery retention screw, gas air inlet cover. That's the one you don't want to soak. Remember, it's not a sampling, it's a gas measurement tool. There's an inlet filter cover that you shouldn't have to remove. There's two different filters in here, and then it goes into the PID before it gets to the other sensors, the toxics and that kind of thing. Charging port cover is that little rubber cover you have to remove. Make sure you remove it if you're going to charge it, otherwise it won't charge. And by removing, I don't mean rip it off the housing. I just mean open it, because those have been broken in the past too. And then your battery retaining screw. There's your gas air inlet and your LED alarm lights. So we'll go through the power on screen. You're going to hold 2 to 3 seconds. It's going to test all its LCD lights. The pump should run. You should hear audible beeps. The lights should blink. And each screen is preceded by a beep. I didn't catch all the screens because they move pretty fast, and I was doing it with my camera phone. So this is the initial startup screen, so you can see that it'll even tell you that this is methane, CH4. Gives you a, hey, my name is Sirius, and this is my monitor. Then it goes to what your cal gas is, which is isobutyl, short for isobutylene. Tells you which battery's in it. If it had an alkaline battery, it would say alkaline. Gives you your low alarm. So every day I look at this, it just reminds me what my monitor is going to alarm at first. So that just tells you that. High alarms. Goes into your short-term exposure limits. That's just like scrolling on the array systems. TWA tells you that it's methane, and those are the numbers. If you were to look at the methane cylinder, it should be 58% methane. It should be 20 parts per million of hydrogen sulfide in that cylinder in our cal station. It should be 60 CO. Gives you your date and time. If those are wrong, let me know. Gives you your last cal date. Next, I wasn't able to capture that on my phone. Gives you cal due, and it gives you the number of days before cal is due. So it'll say 26 days till cal is due. And it'll continue to beep if calibration is due. So it'll move on, but it'll continue to beep. Then it asks you to please wait. That's about 25 seconds. It asks you to zero it. Gives you a pass-fail. After that, and then it gives you your sampling screen, and that should look familiar to everybody. LELs, O2, hydrogen sulfide, CO, and VOC. Any questions? Did we cover everything? Awesome.
And so.
Thanks. Hope you learned something.